lecturing with a real audience and not doing 2 lectures in a row. Um, Before we start today, I just wanted to get kind of a sense from you guys on how the class is going. Now, I'll give you what I feel this is my impression based on the feedback I've gotten in office hours. It seems like the homeworks have been pretty tough and they've been taking up a lot of your time. It's a good thing, but they will be getting slightly easier. Well, I shouldn't say easier, but hopefully less time consuming. Um, I don't have a sense, though, on how things are going with the lectures. I'd like you guys to maybe just, by show of hands, for those of you who think the lectures are going too fast, just raise your hands. Okay, great. So maybe that's 3/4 of the class. How many people feel like it's just right? Okay, and who thinks it's too slow? All right, good. So that's useful feedback. In an effort to slow down today, I'm going to actually recap some of the material from last lecture. Also, I was not in such a good state of mind doing the last lecture, so things weren't so clear to me. I don't know if that came through or not on the tapes. Also, remind me to return the homeworks. I have those with me, homework number 1. Homework number 2, of course, is due this Thursday, and it seems like Thursday is a good day to have homework due, so from now on we'll have homeworks due on Thursday. Office hours are on as usual this week, so tomorrow and Thursday, please feel free to come to office hours if you have questions. We had a makeup session on Monday, and there was a pretty good turnout. Now, did anyone in the class not receive my email about the makeup session? Okay, good. Okay, so let's start. And as promised, we're going to do a little recap. And kind of the topic that we've been looking at for several lectures is this idea that we have this linear time invariant 2-port, and we basically want to understand how we can maximize, let's say, the transducer gain of this 2-port. And had a good discussion in office hours yesterday about what this really means. So for instance, if you could really vary ZS and ZL, well, then you would want to make ZS equal to 0, right? That would be the optimum solution. But unfortunately, in real life, we can't vary source impedances like that. We can't just set them equal to 0. There's always going to be a real part of the source impedance that is physical, because that represents how we're getting power into the system. For instance, that could be the radiation resistance of an antenna. And if the radiation resistance of an antenna were 0, it would receive no power. So you need a real part on the source. You can't just arbitrarily set it equal 0. Also, from the discussion I had in office hours, it seems like voltage gain concepts always seem to predominate your thinking. A lot of you are not used to thinking of power gain. So that's why some of the conclusions that we've come to don't seem very clear. They're more clear if you think about it in terms of power gain. So in particular, we looked at transducer gain, GT. And transducer gain is defined as the power in the load divided by the power available from the source. So this is the power going in the load. And the power available from the source, you'll recall, is the maximum power that you can extract from the source. And that occurs when you conjugately match a load to the source. So in a sense, GT tells us how much better can we do than simply a matched load when using a 2-port. And by application of the maximum power transfer theorem, we know that we can extract the most power out of this 2-port when the output impedance of the 2-port is exactly the complex conjugate of the load impedance, and likewise that we can extract the most power from the source when the input impedance is a complex conjugate of the source impedance. And the way we do this in practice is we take our 2-port and we put matching networks around it to make this happen. So call this M2, call this M1, and this is our source. So last couple lectures, or last lecture, we looked at the design of different matching networks to achieve this. Now, we know that if I look into this port here, I see, let's say, Z in, And by the maximum power transfer theorem, if this is set up correctly, therefore if I look out here, I should see Zn star, right? The complex conjugate of the input. Likewise, from the source's perspective, if I look into here, I see Zs complex conjugate. And of course, looking from the load back, I should see Zl complex conjugate. By definition here, I see Z out. And looking into here, therefore, I should see Z out complex conjugate. So you can see that this matching network is dual. It takes the input impedance and converts it to Z source complex conjugate, or likewise, you can think of it as taking the source impedance and changing it into Z in complex conjugate. Okay? And these, of course, are the matching networks. Now, one of the important points to take away is that it's very hard to do this over broadband because the two-port parameters change as a function of frequency. Therefore, these impedances change as a function of frequency. So it's very hard to achieve this simultaneous input and output match over a wide frequency range. And so usually we actually can only achieve this over a narrowband range. That's the usual way we do the design. So the first matching network that we looked at, just to give you a quick review, is a simple L matching network. And a simple L matching network looks something like this. It's basically two lossless passive devices where this is R low, and looking into this port here, we see R high. Or if we flip the matching network around, right, again, using this concept of duality, if I look into here, it's taking R high and making it a low impedance. So here, I can just explicitly flip that around and say I can take a high impedance and transform it to a low impedance. And we found last lecture that this is actually, this matching network, when we build it with L's and C's, turns into a resonant circuit. And so therefore, it only achieves the matching at one particular frequency, or if you like, it achieves a pretty good match over the bandwidth of the resonant circuit. And of course, the bandwidth of a resonant circuit is driven by its quality factor. So let's look at that in a little bit more detail. So let's look at a particular example. So in this simple matching network, if I imagine that this is voltage V1, then at resonance, what is this voltage equal to? Okay, V1, right? At resonance, the voltage across the capacitor is equal and opposite to the voltage across the inductor. And how about the voltage across this resistor in terms of V1 at resonance? Exactly. So the voltage across here is Q times smaller than the voltage across these reactances. So what you can see is that this matching network is really a resonant circuit that takes this input voltage V1 and steps it down to V1 over Q before applying it to this voltage. So at resonance, we can think of this circuit in an approximate way as a transformer that has a Q to 1 turning ratio, because the voltage gets stepped down by a factor of Q. And if this were a matching network, and if I apply V1 and I apply and observe I1, you would find that the input impedance is Q squared times RLO. Now this isn't exactly the circuit that we've looked at because there's the effect of the source impedance, but now you can see that our exact analysis says it's 1 plus Q squared times R low. And so you get an intuition now for where this Q squared term comes from. Okay? Any questions about this intuition? So the important point is that our matching network, this L matching network, is really a resonant circuit. You can see here it's a series resonant circuit. And it's this property of series resonance, where the voltage across the reactances is Q times larger, that really achieves the matching for us. Well, if we look at if we flip around the L matching network, then it looks something like this. So in this case, this is R high. And now this looks like, if I imagine a current going into here, let's call this I in, then this looks like a parallel resonance circuit. So I know at parallel resonance, this current in this inductor is equal and opposite to the current in this capacitor. And I also know that at resonance, the current going into this resistance is Q times less than the current going into my reactances. So again, I have an equivalent circuit now that looks like a transformer, except the windings are flipped around. And that means the input impedance is R high over Q squared. Okay. Any questions? So I'm just imagining that this is in some parallel resonance. So let's say I drive this with some current source, right? Then I know that at resonance, these currents balance out, right? And then a small current, which is flows through this resistance. That makes sense? So the idea is that this current has two components to it. It has a reactive component and it has a real component. Real component for a high Q circuit is much smaller. So here we're making an approximation of a very high Q circuit. But you're right, it doesn't follow KCL. It's a high Q assumption. Okay, so what are the limitations of these simple matching networks? Let's say of the L matching networks. Well, one is the Q, or the bandwidth, is really set by the matching ratio. In other words, for instance, Q is always the higher impedance over the lower impedance minus 1 square root. So the quality factor is not a free parameter. Which means the bandwidth is fixed. So if you design a matching network and the bandwidth is not what you'd like it to be, you have no choice. The other issue with this matching network is the loss is a strong function of the Q of the network and the Q of the components. And last lecture we derived approximately that this expression is true, that the insertion loss goes like the ratio of Q over Q of the components. Now, just to give you an idea of what you get if you go out and buy inductors or capacitors, capacitors are usually better than inductors. Inductors are usually the lowest lowest Q component. So we'll say that inductors dominate losses. So for instance, if you build an on-chip inductor using metal layers, your Qs are going to be on the order of 5 to 10. Maybe a little better, maybe a little worse, depending on the process. Very strongly dependent on the process. And the way you build inductors is you just wind. You basically use planar spiral structures like this to build inductors. Higher frequencies you can use transmission lines, but at lower frequencies you have to do something like this. And because you don't have magnetic materials in a standard process, these inductors can range, let's say, from hundreds of picohenries to at most 100 nanohenries. But realistically it's more like 10 nanohenries. So this would have an SRF, self-resonant frequency, below a gigahertz. On the other hand, if you go and buy a chip, Q, let's say an air core inductor, and it's an expensive one, you can probably get a Q of 30 to 50. And if you can't afford to pay for these high Q inductors, then probably your Qs are going to be 15 or so. And so this is kind of a fixed when you're doing your design. And if it turns out that the Q of your circuit is very high relative to this component Q, that means your circuit is going to be very lossy. Okay. Now, last lecture we did kind of a funny derivation of this formula. Funny because probably not everyone probably understood it. I could give you guys a very simple derivation, which is probably a little more intuitive, and then you can see where the more general derivation comes from. So here's the simple intuitive derivation. This is my load, and this is, let's say, my finite Q inductor. So this is my non-ideal inductor. So it has some series resistance we'll call Rx. Now the insertion loss, since this network here is lossless, I can see that the current going into the load will produce loss because of this resistance. So if I write the insertion loss as the power to the load divided by the total power dissipation, let's call this Px, the power lost in this resistance. This is simply 1/2, let's call this current I squared RL divided by 1/2 I squared RL plus Rx. Okay. Any questions or comments up to here? Yes?
Can you use bond wire for inductors for the RF application?
Yeah, that's a good question. Coming back here, bond wires are increasingly used, and they have Qs from 20 to 30 and inductances on the order of nanohenries, few nanohenries. The problem with inductors is their value is not very precisely controlled, so they vary a lot. You put down a bond wire. First of all, just an aside, what is a bond wire? So a bond wire, of course, is the wire that goes from your chip to your package. And this wire, I didn't do a good job actually of drawing this. I should have drawn a much smaller chip. This wire has inductance. And the inductance of this wire, actually you can only define the inductance of the bond wire if you define a loop. But let's say I define this loop as I've shown here. Let's say I short this end and on chip define this loop as forming my inductor. If I do that, then this inductor will also include these leads. If I want to get rid of these leads, you might imagine maybe putting some bond wires here too. But the upshot of it is that if you bend these, if I just take a screwdriver and move this, let's say, and do something like that, the inductance changes. And so the inductance varies a lot. So I have to come up with a way of dealing with that variation. And one way to do it is switch capacitors, which we probably will talk about a little bit later when we talk about VCOs. Okay, so coming back to the calculation of the insertion loss, we see we have a very simple formula. Current just drops out of this equation. And so I can write the insertion loss as 1/1 plus Rx over RL. Okay? Now what is Rx? Rx is omega L over QC by definition. And what about RL? Well, RL, remember, is related to L through the Q of the circuit. And so if I substitute here, I get 1/1 plus Q over QC. And so because Q depends on the matching ratio in a square root fashion, you can see that if you have a really large matching ratio, you're going to run into trouble. So for instance, let's say you do something naive and you say, I want to match the gate resistance of this transistor to 50 ohms. And let's say the gate resistance is, let's say, 1/2 ohm. So that's a large matching ratio of 100, requires a Q of 10. If I try to do that with an on-chip inductor that has a Q of 5, I'm going to get so much. This formula, first of all, won't be valid. Well, it is valid for this simple case. But the formula we derived last lecture, that general formula, is not valid. And you'll find that you have quite a bit of insertion loss. More than half your power, if not more, is going to be wasted in this matching network. And so the whole point of putting down a matching network was try to get more power gain. You can see that you're going to run into trouble. So simple matching networks are great, but they don't have flexibility. Okay. Any questions? Yes.
So one of the reasons you last lecture mentioned about the inductive degeneration common-emitter amplifiers, the main reason for that is to synthesize the real impedance for the input. Is that reason you cannot use L match or pi matching here? I have to use inductor.
That's part of it. Yeah, that's exactly right. So there's other ways of doing it. So for instance, if I look into the gate here, there's also a lot of capacitance. So if I turn this into so the equivalent circuit looking into the gate here is like this. So this is a small resistance. Well, if I put an inductor here, and resonate this out, you know that this is equivalent to L C prime and R large. So this is another way to synthesize a larger value resistance. Just put an inductor in shunt. The other way is what we saw last lecture of using inductive generation. But think of this as an aside. We're going to come back to this topic later on. Any other questions? Okay, so last lecture we also started looking at other matching networks, in particular the T-matching network. And the idea for the T-matching network is I'm going to take a low impedance and I'm going to basically use an L-matching network to bring it up to some intermediate impedance, which is actually larger than what I really need. So I'm going to overshoot, if you like. So then I'm going to use another L-matching network flipped over to bring it back down to, let's say, R high. And then I'm going to connect my source with impedance R high here. And because these two caps are in parallel, you see they combine, and the overall matching network looks like a T. Okay? Now, let's derive what the quality factor is of this matching network. And the key to doing that is to take this center point and transform the left-hand side and the right-hand side into parallel equivalent circuits. So let's start out with the left-hand side. So this C is already in parallel. Let's call this C2L2 and this C1L1. Okay? So if I transform this series element into a shunt element, this becomes L2 prime. This becomes 1 plus Q squared R low, which by definition is just Ri by design. And now I do the same thing for the left-hand side. I take this series element, transform it into a shunt element, and it becomes L1 prime, and R high multiplied by 1 plus Q squared, which is again Ri. So this is the center point. Now, I can define the individual quality factors for these networks. For instance, the quality factor for network 2 is omega C2 divided by Gi, right? This is the quality factor of this network. It's a parallel network. Quality factor of this network is omega C1 divided by Gi, where Gi is just 1 over Ri. Correct? So how about the quality factor of the overall network? Well, for the overall network, I just put the C's in parallel and the L's in parallel. So the quality factor of the overall network is C1 plus C2 divided by twice the conductance, because I have two resistors in parallel. And of course, you guys recognize this as 1/2 omega C1 over Gi plus omega C2 over Gi, which is just 1/2 Q1 plus Q2. And so we see that because Q1 and Q2, remember Q1, R high is larger than, Ri is larger than R high, so Q1 is Ri over R high minus 1 square root. Q2 is Ri divided by R low minus 1. And so you can see that this expression is just a function of Ri, which is a free parameter. R high and R low are fixed. That's the matching problem that we're trying to solve. So I can basically achieve any Q I want by just choosing Ri appropriately. Okay, questions or comments about this? Notice that in general, though, the Q is going to be larger than what I would achieve with a simple matching network. So this T network lets me achieve very high Q matching. Okay, well, the analysis of the pi network is equally simple. So we have a pi matching network. It's really the same idea, except the other direction. I start out with a high impedance. I transform it, let's say, to a low impedance, whereas at this point, Ri is actually less than the R low that I'd like to achieve. So then I have to connect another matching network to transform it up again. Let's call this L2, C2, and now I'm at R low. So if I now do the opposite, if I convert this into a series LCR circuit and this also into series LCR circuit, I have that this is equivalently L1 C1 prime Ri. This is L2 C2 prime Ri, where I'm doing a parallel to series transformation. And this is the midpoint again. And now, for this circuit here, I know that Q1 is omega L1 over Ri. You can see that from this equivalent circuit here. And the Q of this network here, which is the same as the Q of this network, Q2 is omega L2 over Ri. Okay. I'll stop here and take any questions. Okay. Now the Q of the overall circuit is not too difficult to see because these two inductors are in series, is omega L1 plus L2 divided by the total loss in the circuit, which is just 2 times Ri, which again works out to the same formula as before, 1/2 Q1 plus Q2. And so we see that the pi network is the dual of the T network. Again, it lets us choose this intermediate impedance as a free parameter to achieve the quality factor that we want. In general, the quality factor is larger than we would achieve for a single L matching network. Okay, any questions? Let me remind you that we also could do reactance absorption. And these formulas that we've looked at, we've only derived for real loads. So what if you have complex loads? So for instance, this is a very common complex load that has capacitance on it. Well, I can use an inductor to first resonate out this capacitor, and then I can design an L matching network because now my effective load is real at resonance. And then, of course, I can absorb this extra inductance into here. And notice I didn't have to use an inductor here. I could use also a capacitor. And so then I either end up with a capacitive transformer or an inductive transformer based on the values of these various elements. So in general now we have a procedure that lets us design L matching, pi matching, and T matching networks for basic complex sources and loads. Okay. Well, before we go away from matching networks, let's look at one more matching network. Let's look at a multi-section L. And we'll find out that this allows us to design lower Q or higher bandwidth circuits. And I introduced this to you guys last lecture, but let's recap. So let's say I have a single L matching network, and instead of transforming directly to R low in one step, I do it in two steps. So here's step one. At this point, I have some intermediate impedance which is less than R high, but it's still greater than my desired R low. So then I have to put in another matching network to get to R low. So at this point, I get to R low, and I want to show you guys that this actually does introduce a lower Q circuit than a single L matching network. Okay? Is this clear to everybody? So now looking at this circuit, if I want to simplify it, I can try to use the same trick that I did before. I can turn this guy into a series LCR circuit, where this is Ri, this is C prime, and this is L. Let's call this L1C1. And this side, I turn it into a parallel matching network. So this is C2. This is L2 prime now. And this is also Ri. Now the key observation here, when analyzing this circuit, is that at resonance, there's a current flowing through here that just precisely balances out. So the current going into here, which is the current that goes into this resistance, is the same as the current going into this resistance. So the same current, real current, is flowing through this resistance and this resistance at resonance. Another way to see that is at resonance, this balances out, so they cancel each other out. So at resonance, looking to the right, I just see Ri. Looking to the left, these two resonate each other away, they're gone, and I just see Ri. So this is the equivalent circuit at resonance. Okay? And so that means the power dissipation is the same in both networks at resonance, right? I have a current flowing through here. I squared Ri 1/2 flows here. I squared Ri flows here. So the power dissipation in both of these circuits is the same. So I can say that the power dissipation is the same in both circuits. And so now, if I want to find the quality factor of this entire circuit, I can say that the quality factor is the power stored, the energy stored per cycle, divided by the energy lost per cycle. So the energy stored is the energy stored in the first network and the energy stored in the second network. And the power dissipated is 2 times PD, where PD is this power that we find that's dissipated in these resistors. Well, this is really simple. I can just write this in the following way. And so now I have 1/2 Q1 plus Q2. Same formula as before. But we're going to find that this is actually a little bit different. The difference is that if I look at Q1, Q1 is R high over Ri. Minus 1 square root. Q2, on the other hand, remember Ri is larger than R low, so Q2 is Ri over R low minus 1. So now in this expression, you can see that Ri, the intermediate impedance, appears in the denominator here, appears in the numerator here. Whenever you see an expression like that, you get the sense that there could be an optimal, right? There could be an optimal impedance that will result in a stationary point for the Q. So let's derive that optimal impedance, take the derivative of the Q, set it equal to 0, what you find is it's a minimum, a local minimum, and the optimal solution to achieve that local minimum is the geometric mean of the high and low impedance. So if you want to design a matching network that has the highest impedance possible, and you want to use 2 stages, you should take the geometric mean as the intermediate impedance value. Now, you guys can see that this concept easily generalizes to more than 2 stages. I could go 3 stages, 4 stages, and I can keep decreasing the value of the Q, or increasing the bandwidth of the matching network. We won't do that. It's a simple extension. In practice, you probably would not want to do more than 2 stages because things get pretty complicated and ugly. Okay? So I hope you can see now that the concept of resonance, the concept of matching network, and the concept of amplifier design have all come together. When we design an amplifier, we found that doing resonant amplifiers was a nice way to get rid of parasitics. It allowed us to go to higher frequencies. We also found that to design amplifiers, we like to change the source and load impedance to the optimal value for the 2-port. We found that L matching networks and pi and T matching networks can do that, but those are also resonant circuits. So in practice, we usually combine the matching network and the resonance. So let me show you an example. So here's my amplifier. Okay. So first of all, I need to bias this. I need to apply a DC bias. So usually at RF frequencies, a convenient way of providing bias is either through a large resistor or through an inductor. So let's say I use an inductor. So I'll call this V gate, and I'll put an inductor here connected to VDD. Okay. Well, then you say, wait a minute, why don't I just make this, instead of making this a very large inductor, so you'd use a choke to bring in a DC. A choke means a very large inductor. Instead of using a large inductor, why don't I just make these inductors the right size that can resonate out the capacitances on this device, right? And yeah, you can do that, but in fact, it's probably better if you add some capacitance to this device. So for instance, it would be better if I added some physical capacitance here, because then the capacitance of this drain, which varies over process, could get swamped out by this larger capacitor, which has much better process control. So this is a larger capacitor that I introduce, and so then I choose the L to resonate with this C. And I can do the same thing on the input. But usually if I'm going to be driving another stage, I'd like to have AC coupling. So instead of having a capacitor like this, why don't I put the capacitor in series? Like that. Now this is an AC coupling capacitor, but it also is in series with another capacitor here, and this sum capacitance resonates with this L. Well, I can go a step further. I can say, well, this could be a matching network. So instead of just making it resonate, I can choose L and C to transform this low input impedance to a high impedance that likes to be seen by this device to get optimal power transfer. So really this becomes an L matching network. And now you can see that these components are serving several functions. It's serving as a biasing element, it's serving as a DC isolation element, it's forming a resonant tank, making this a narrowband amplifier, and it's forming as an impedance transformation function. Okay, later on we're going to actually spend some time talking about low noise amplifier design, and we'll see some of this in practice. You'll also see a lot of this in practice when you do homework. In fact, you've already been exposed to that in the second homework assignment. Okay. Any questions, comments? All right. I'm going to start a new topic. We're going to talk about distortion. And let me just give you guys a little bit of background on distortion. If we take a typical amplifier, and we apply some input signal and look at the output signal. This might be voltage or current, this might be voltage or current, or this might be power, and this might be power. But in general, we draw this little triangle to represent our amplifier, and we usually, in courses like 140, we look at the small signal characteristics. But, you can go in SPICE, or if you can do the math, you can actually derive the large signal characteristics. In other words, you can derive a transfer curve, and for a lot of amplifiers it looks something like this. If I keep increasing my input, the output increases in step initially, but eventually it saturates for positive and negative signals. And so what we like to do is we like to operate our device in this region. We call this the linear region. About this operating point, it looks pretty linear, but the question is, what happens if your input signal is large enough to take you a little bit into this region? What happens to the output signal? Well, as we'll see, we're going to get what we call distortion products, or new frequency components that are in the output which didn't appear at the input. And these different distortion frequency products can be very annoying. For instance, if this is an audio amplifier and you put in music here and the output has frequencies you didn't intend to be there, you're going to hear it and it's not going to sound good. Well, if you're an electronic guitar player, maybe you like the sound of distortion. But usually we like to faithfully reproduce or replicate the input signal with just a larger amplitude. And so this distortion can be bad. In this class, we're going to consider what we call memoryless distortion, or memoryless nonlinear systems. And that means that we're not going to look at this transfer curve is going to be static. It's not going to vary as we increase the frequency, and it's not going to have any weird hysteresis in it. We're just going to assume that the nonlinearity of the system is due to DC nonlinearities of the device. Now, as that'll become more and more clear as we go forward. So the idea is that this thing has no memory. If I apply to it a signal at time t, and then I look at the distortion that's generated, and then I do the same thing at t plus delta, the distortion will be the same. The previous input signal does not influence the distortion generation later. Now right away you say, well, that's a huge limitation because any circuit with an L or a C, right, has memory. So this would strictly only work with resistive circuits. But we'll see again in this class that this is a good place to start, and if we're careful, we can actually de-embed the memory from the circuit and apply it separately. Okay? Questions? Yes?
So you said we want to operate in the linear region, but I thought we want to design amplifiers so we can operate and swing them from rail to rail.
Okay, there's conflicting requirements. If you're designing an amplifier and you're trying to maximize the power capability, you would try to go rail to rail. But as you do that, you're going to generate a lot of distortion. We'll see that in this class, so there's a trade-off. Okay, so let's make some assumptions. So our assumption is going to be that we can describe the input and output characteristics with a power series. In other words, we assume that this curve is smooth and continuous. So if we look at the output signal, we can write it as basically a linear term, that's the linear gain, plus some second order term, third order term, and so on and so forth. So if you like, in general, the output is some general function of the input, and we're doing a Taylor series expansion. And we're getting rid of the DC. So we're getting rid of the DC operating point, and we're only looking at the AC terms. So in general, S output as a function of S input, what we do is we apply some DC plus some small signal voltage, and then we do the Taylor series expansion. This is f of DC plus f prime evaluated at DC times S input plus f double prime at DC divided by 2 factorial times S input squared plus higher order terms. Now, if you're a mathematician, you know that it's kind of, to define when you can do a power series of a general function is actually a pretty complicated affair. If you take a course like Math 105, you'll learn that you can actually dream up continuous curves that don't have derivatives anywhere, and so that you can't do Taylor series expansions about them. In this class, we're going to just safely assume that most things we deal with are nice and smooth, and we can do Taylor series expansions. So let's give a simple example of that. So if I look at the collector current of a bipolar transistor as a function of VBE, I know it has an exponential characteristics. So this is IS e to the q VBE over KT. And usually we pick an operating point. That's our DC point. We'll call this VBEQ. And now we operate about this operating point. Usually we assume that the circuit is linear, so we take the slope here, and that's our operating point. But now, instead of assuming that it's just a straight line, we're actually going to take this curvature into account. And we can do that by simply taking a Taylor series expansion about VBEQ. So the important point is that we don't care about this DC value, IQ. So what we do is we shift the curve. So we plot IC minus IQ versus a small signal input, and then this curve basically shifts to the origin. And then we take the Taylor series expansion of this function. Okay? So that's one example. What about a MOSFET? So I guess I should be titling these things. BJT distortion. How about MOS distortion? Well, same exact procedure. For a MOSFET, if I plot IDS, so here's my device, here's the small signal input, here's VGSQ, and then I'm going to observe the output current, then I know that a very simple model will do something like this. This is VGS, and this is square law. If I actually zoom in around the threshold, I know that it's more complicated. It's actually exponential in this region. But for now, let's just assume that that's the case. I'm also going to operate my device in forward active region, let's say. So I'm going to operate somewhere here. So the output approximately does look like a linear resistor. But if you really want to be good and capture the whole nonlinearity, then you'd also want to capture the curvature here and see how that changes things. But let's keep the problem simple for now, and we'll make it complicated later. So if we keep it simple for now, we know that if we have a square law model for the device, the current goes like VGS minus VT squared, 1 plus lambda VDS. So we're not including the nonlinearity of the output. We're assuming linear output. But you can now see that I could generally add terms here, nonlinear terms, to try to capture the nonlinearity of the output. Okay, any questions? So again, we do the same exact thing. We assume that we operate it at some VGSQ, and we do a Taylor series expansion about this point and try to capture this curve. And you can see that for a simple MOSFET model, this is just a parabola. So we only need simple polynomial, up to second order polynomial, to capture this device. But that's a huge approximation. It turns out that for most low power operation, you don't want to operate too far in strong inversion. You much rather operate in what's called moderate inversion, so closer to here. And if you move close to here, then that subthreshold behavior is going to be very important. And if you look at the curvature of the device here, it certainly does not look like a parabola. It looks something between an exponential turning into a parabola. And so at this point, the nonlinear model is much more complicated. Also, if you look at the output impedance for a modern short channel device, it's not nice and flat like this, right? It actually has lots of curvature. And so this will also complicate things. Questions? All right, one of the most important devices that we'll study is a differential pair. So a differential pair is a very nice building block. Ideal differential pair has a constant current, and we're going to assume that we apply a perfect differential signal to the input. So half the input is here, and the other half of the input is over here. And we're interested in the differential current, IC1 minus IC2. So the input voltage, you can see, is VBE1, let's call this Q1, this Q2, minus VBE2. So if I go around this loop here, I have that the input voltage is VBE1 minus VBE2. And I know the individual collector currents are exponentially related to VBE1 or VBE2. I also know that the sum of the currents has to stay constant, because the sum of the currents go into a current source that keeps that current constant. So using these three equations, I can derive the large signal transfer characteristics. So the output current, which is defined as the differential output current, or the difference between IC1 and IC2, you can show that this is alpha times IEE, that constant current, times the hyperbolic tangent of the input voltage normalized to KT. Okay? And if you plot that, that has this characteristic S-shaped curve. And the limiting values are very obvious. Clearly, the most output current I can get is IEE, because IC1 and IC2 are basically limited by IEE. So if I drive my differential pair very hard, then all the current goes to one side, and so I get a total current of IEE or minus IEE, depending on how hard I drive it, in which direction I drive it. Okay? And the range over which this happens is a function of KT over Q, about 120 millivolts. So very small input signal, plus 60, minus 60, I can actually saturate this device completely. And of course, you can see that this device, the differential current, already is in a nice form. It's already biased at 0, so now I can do a Taylor series expansion of hyperbolic tangent and do my analysis. Okay? Pretty clear up to here? All right. So let's do some examples, and it'll become a lot more obvious what we're doing. But let's actually look at this power series and see what happens for a sinusoidal input. So we can see that in general we have a representation that looks like this, basically a polynomial. A1 is the small signal gain. In other words, when S input is very small, then S input squared is even smaller, so this term is negligible compared to this term. S input cubed is even smaller, so this term again dominates. So for very small input signals, this term dominates, and A1 is the small signal gain. Also, it's important to note that A1, A2, A3 are independent of the input signal. They depend on bias, temperature, and the basic characteristics of the device at hand. All right. Let's look at the idea of harmonic distortion. So we're going to take an input signal, call it S1 cosine omega t, a sinusoid, and we're going to put it into this system. Now we know that a linear system would just take this and gain it up and maybe add a phase shift to it. But if it's a memoryless system, the phase shift will be equal to 0. So it just takes the input and produces an output. This is just the amplitude of the signal. Yeah, it's just a bit of notation. We use S because it's a signal. It could be voltage, it could be current, and so on. On the other hand, a nonlinear system will produce A2 S1 squared cosine squared omega t plus A3 S1 cubed cosine cubed omega t and other higher order terms. Now we can simplify this using a little bit of trigonometric relationships. Cosine squared, I can write that as 1/2 1 plus cosine 2 omega t. So we see that when we square something, we generate a DC term, and we generate a term at twice the frequency. And we'll find in general that when we take even powers of sinusoids, we generate DC and even harmonics of the input signal. Jumping ahead a little bit, simplifying this cubic term, or expanding it rather than simplifying it, this generates a third harmonic term and a fundamental term. And then we have the higher order terms. So you can see that things are getting very messy. If we look at let's say the fourth harmonic, we'd find that it also generates a fourth harmonic. If we look at the fourth power, rather, we see that it generates a fourth harmonic, a second harmonic, and a DC term. A fifth harmonic, fifth power, will generate the fifth harmonic, third harmonic, and fundamental, and so on. And we'll prove that in a moment. But these terms here are called harmonic distortion. They're called harmonic because they appear at harmonic frequencies of the input. In other words, multiples of the input frequency. And they're distortion because they're not supposed to be there. Okay, any questions? So let's summarize that. So we could say the term A1 S1 cosine omega t is the wanted output. We have higher order harmonics generated. We call these distortion. And they appear at frequencies 2 omega, 3 omega, DC even, and we'll see when that is important, and also at omega. Right? So we had a distortion term that came in at omega. You might say, well, that's not distortion. Later on, we'll see that this actually can be distortion when you have more than one frequency present. Okay? The other interesting thing is that we found so far that the second harmonic produces a DC shift. Because the second harmonic produces a DC output signal, we can see that the output current DC level will go up due to second order distortion. And that may be bad in many applications. we could always put a low frequency feedback loop around our amplifier to stabilize the current, and that would get rid of this DC shift. Okay, so the third harmonic, this should be the second power. Third power produces omega, 3 omega, and so the phase of omega term is important, because if it turns out that the cubic or third power is generating fundamental with different phase than the regular output, that could subtract from the input and actually reduce the gain of the amplifier. Okay, so this term will either generate gain expansion or gain compression. Okay, so for instance, if I look at this curve, the gain is the slope, right? Now if I have a signal that takes me part way into this compressed region, if I have a large signal, you can see that the slope here is less. So intuitively, you would imagine that the larger I make my input signal, the less the gain is. The gain starts to get compressed. At the peak, at this origin though, I have the peak gain because the slope is maximized. On the other hand, if I have a curve that looks like this, physically it has to eventually compress. But let's say it looks like this in a region of operation that I care about, then you could see the slope here is actually larger than the slope here. And so if I have a large input drive, it experiences higher gain some of the time than it would if you had a small signal. That's called gain expansion. All right, questions? Yes, Vincent.
Just curious, is harmonics necessarily a bad thing? I think of applications like music where you have single tone, as long as multiple integers of the frequency, you can get richer music or something.
It's a bad thing in terms of, I mean, what's the purpose of an amplifier? An amplifier is supposed to amplify the signal. It's not supposed to change the information content of a signal. Later on, we'll see that if you put, let's say, so one way to look at it is if you put video through an amplifier that has a lot of distortion, and then you see that video, obviously it's going to be ugly. In fact, if you guys really have a lot of energy, you can go in MATLAB, take an image, represent it with a digital signal, put it through this nonlinearity, and then recreate that image. And you'll see actual visual blemishes due to this distortion. So in general, it's bad. Now, there are certain cases where we like distortion, but that's artistic. We're engineers.
Question:
yes.
What are the axes of the gain curve?
So this is the input signal. This is the output signal. Okay. All right. So another thing that we can look at, I'll just getting lazy, so I'll use a slide here. You zoom in on the top slide. So this is, let's assume that I have this fundamental, as I've shown here, and I just add some second harmonic to it. You can see that for this particular phase of second harmonic, what it's going to do is it's going to subtract from the signal here, so it's going to actually make the peak lower at this point, and it's also going to fatten out this peak a little bit. And on the other hand, over here, the second harmonic is now in phase with the signal, so it's going to actually make its peak larger. So the overall waveform, due to second harmonic, if you're looking on a scope and you're trying to visually detect if there's second harmonic or not, this is one way that second harmonic shows up. It makes one peak fat and one peak skinny. On the other hand, if we look at third harmonic, so what I did was I took a sinusoid and I just added a third harmonic signal to it, you can see that the third harmonic will add, it's in phase at these 2 points, but out of phase at these 2 points. So it adds 2 little peaks here, but subtracts here. So it produces this square-like waveform. So if you look on the scope and you see something that looks like this, you can tell right away that there's lots of third harmonic present in the waveform. Well, this is one phase of third harmonic. What I can do is I can change the phase of my third harmonic, and now I'll have a waveform that looks like this. If I phase it like this, then you can see that both here and here, the signal is always in phase, so it's adding to the peak and making the peak higher, so I have more voltage swing. But unfortunately, it subtracts from these skirts here, so it makes it more narrow. So this is another way of detecting third harmonic, is more triangular waveforms. Okay? Yes?
So, our voltage transfer curve kind of looks like an odd function. Does that mean the A even terms are really small, and we should have even order smaller?
Yeah, that's a very good observation. So remember, if I have a waveform that looks like this, this is an input, this is the output. This is an odd function, right? Meaning that the output on the negative side is a flipped version of the output on the positive side. So this is an odd function. Mathematically, f of minus s input is minus f of s input. And you guys know that if you do a Taylor series expansion on an odd function, you only get odd powers. So if you go back and look at that differential pair, intuitively the differential pair should be an odd function, right? There's no reason why it prefers one side to the other if the devices are sized the same. So let me draw that. So a diff pair, without doing any mathematics, I'm convinced that it has to be an odd function if these transistors are identical. Therefore, I can say, without doing any math, that a differential pair generates no even distortion. So it has no even powers in Taylor expansion. Okay?
I had a follow-up question, sorry.
Okay.
So basically this means we never have to worry about DC offset.
Yes and no. In reality, you never get two identical transistors. So the fact that these transistors are a little bit different always generates some second harmonic in this circuit. And that's the matching problem. Okay, so let's go back to this general distortion. In other words, we found cosine squared, we found cosine cubed. What we're interested in is cosine to the nth power. And we can write that as 1 over 2 to the nth power, e to the j theta plus e to the minus j theta to the nth power, using a complex expansion for cosine. And of course, I can expand this using a binomial formula. So this is a sum from k is equal to 0 to n choose k, e to the j k theta, e to the minus j n minus k theta. Okay, that's a simple application of binomial theorem. And remember, these coefficients form the Pascal triangle. So if you ever want to calculate this product out, you can just draw a little Pascal triangle. So for instance, for n is equal to 3, let's see what we get. So 2 to the third power is 8. We have 3 choose 0, e to the minus j 3 theta, plus 3 choose 1, e to the j theta, e to the minus 2 j theta, plus 3 choose 2, e to the j 2 theta, e to the minus j theta, plus 3 choose 3, e to the j 3 theta. And remember, binomial coefficients are symmetric. So the first coefficient's equal to the last coefficient. These two inner coefficients are also the same. You get that from the Pascal triangle, right? Pascal triangle is also symmetric. So if you look at this carefully, you can see that you can group terms. This is equal to this. So I get a term that's sum of e to the j theta and e to the minus j theta. And when I sum them together, I get a cosine 3 theta. Likewise here, you can see that these two coefficients are going to be the same, and therefore it looks like I have to do a little more work on this one to show it, but essentially, let me group terms here. If I multiply this out, this gives me e to the minus j theta. This one, though, gives me e to the plus j theta. So if I group these two terms, I get a cosine. So let me just write it out longhand so it's perfectly clear. I have e to the minus j theta plus e to the plus j 3 theta, and the coefficient on the upper and lower term on the Pascal triangle is just 1. The inner coefficient is 3, 2 plus 1, e to the j theta plus e to the minus j theta. And so this simplifies to 1/4 cosine 3 theta. If I divide and multiply by 2, do the same thing here, and I get 3/4 cosine theta. Okay, so that's not very interesting because we already knew the answer for the cube. What is interesting is if we look at the general expansion. Okay, so let's look at, for an even power, what happens. For an even power, let's look at the middle term. So in this general binomial expansion, right at the middle, the power is 2k, and I'm looking at the kth term. And in the binomial expansion, there's a nice symmetry here because I have e to the, let's say, n, and then e to the n minus m. Because it's the middle term, n minus m is also e to the n, and so this turns out to be e to the minus n. So you can see that I get this balancing act, and these two terms cancel out. So now we see that even powers generate dc. This never happens with odd powers because in the odd case there is no midpoint. Is that clear to everybody? If not, you can spend a few minutes with this and convince yourself. Let's look at the general case. So the general case for a binomial expansion, the general term, when we expand this, we have a sum of terms that look like n choose k, x to the n minus k, x to the minus k. And this is n choose k, x to the n minus 2k. So this term generates every harmonic possible, right? Between basically possibly the 0th harmonic if we have an even power, but it generates, as we run k through all possible values, we see that this general power term generates every harmonic. So this term n choose k, x to the n 2k generates every harmonic, every other harmonic, because of the fact that there's this 2k in there. So this is going at a function of 2, so it's generating, let's say, first, third, fifth, and so on. If it generates dc, it would generate dc, second, fourth, sixth. So now we come back to the question that Kevin asked. So for a odd function, f of minus x is equal to minus f of x, f of x Taylor series expansion has only odd powers. That means that this will only generate first, third, fifth, and so on. Because if we come back to this expression, here we see that there is no midterm, so we don't generate DC, we generate first, and then we generate the third, and so on and so forth. Now an even function, let's say g minus x is equal to g of x, when we do a Taylor series expansion, has only even powers, and so it will generate DC plus every even harmonic of the input waveform. Okay? Any questions?
If the input is not sinusoidal, would you get harmonics?
Okay, good question. So why are we even looking at harmonic outputs? You know, in general, we don't have harmonic signals. Well, several ways to answer that question. One, we know by Fourier analysis we can always decompose any signal into harmonics, right? But it gets very complicated because we just looked at putting a single tone into our nonlinear system, and we see that all these harmonics are generated. Turns out if you put multiple tones into the circuit, not only do you get harmonics, but you get intermodulation products. We'll see that next lecture. So the analysis gets really complicated. We'll look at it, we'll touch upon it. But the reason that we are, in general, looking at the harmonic response is that most communication signals are narrowband, meaning that there's one tone that's predominant, and there's a small modulation term, small in frequency, that generates other tones, but usually it's a very small bandwidth. So the fractional bandwidth might be 1% or 0.1%. And so that effectively, to the circuit, it looks like we have one tone present. Okay, good question. Anything else? Any other questions? All right. So if we now look at the output waveform, it has some fundamental in it. It has some second in it, possibly. It has third in it, and other higher harmonics. And if we go out on a spectrum analyzer is a device that lets us look at the different frequency components in a signal. It basically shows the spectrum of our input signal. If we look at how much signal is present on the spectrum analyzer, one of the interesting things we'll see is that the rate at which the second harmonic grows is different than the rate at which the first harmonic grows. In other words, let me first make the plot and then walk you through it. So this is a plot of the fundamental at the output. So if I have a small signal and I keep increasing it, the output increases and eventually it compresses, right? This is what we talked about early on. This is the gain compression. Now if I look at the presence of a second harmonic, it's going to be way down here. Let's say this is a log scale. So no matter how small I make the signal, there's going to be second harmonic. It's just going to be very, very tiny. But the rate at which the second harmonic grows, we'll find, is actually faster than the third harmonic. So as we go to larger and larger input signals, we get to the point where the amount of second harmonic that's present is actually very much similar to the first harmonic. Very gross distortion. Likewise, if I look at the third harmonic, so this is VO2, it's even smaller, but unfortunately the rate at which it grows is also much faster than linear. And so it will also catch up to this signal. So next lecture, we're going to look at the rates of growth of these harmonics and characterize the nonlinear system. Okay, before you leave, pick up your homeworks.